A week before the exam.
Really?
Here we go, questions.
That's,
Yes.
you put the 3 on the 22, fall 22 exam.
I'm saying 37.
I remember that. I think it's been 2 weeks.
This whole actually made you through it. I'll jump.
Okay, so this is one about where I give you the 3 basis elements, V and or talk about linear transformation. So,
I might mostly the same. I probably agree. All right. You would do that. I would. So. Have a good day. Yeah. All right. I'm building. Okay, that's when it starts now. When it starts. What?
I guess they're usually.
well, all right then.
I need a 35.
I voted for
That would be. Who's got our?
Oh, shoot. I just have a better.
I'm sitting right in the back, which I am fine with.
His average on the final was 54. That was good.
No, it's not. Okay.
So, we've got these vectors here, 3, 1, 2, 3. Okay, so there's your 3 vectors. You may assume that this is a basis for R3. Of course, you could verify that, but don't when I see you can assume it. Okay, so let T from R3 to R3 be the linear transformation. Given by T of V equals PV. Someone call this base. This is the basis here. Funny B. What is the matrix? And this is a transformation in B coordinates. Okay, so number A, find a matrix says that P changes standard coordinates to B coordinates. How we're going to do that? Okay, find P. P standard coordinate to B coordinates. Yes.
Would it just be the basis for B? Like the 3 vectors it gives you?
You mean like 1, 0, 1?
Yeah.
Actually, the other way around. Because that matrix will change B coordinates to standard. Right. So what you really want to do, I think. So you're trying to change B. I think the book uses this notation, B the standard, right? 101. 1. And what should I fill in on that side for standard?
Yeah.
The identity matrix. So what is this algorithm really doing?
It's finding the
It's
inverse.
finding the inverse of this, and if this changes B to standard, the inverse will change that, so it's all coming together. So I need to turn this side into the identity, right? So. 1 minus 1, 0. I'm gonna leave this alone. And I'm gonna multiply this by -1 and add it here. Oops, go on one side. I'm gonna multiply this by -1 and add it here. It's gonna be 0, 2, 1. And multiply this by -1 here. Okay, so far. I'm gonna. I mean, I could divide out and use my fractions, but I really hate to do that, and this is gonna be easy. I'm gonna just, take -1 times this and add it here. Right, because that's gonna be 0, 1, 0, that's all convenient. And so what did I do? -1 times this plus this, -1 times this is 1, 1 minus 1. And I'm gonna leave the top alone in this step. Now I'm gonna use that middle row, the 0, 1, 0, to take everything out above and below it. So I'm gonna leave 0, 1, 0. Right. 1, 1 minus 1. Now to take out what's below it, I'm multiplying by -2 and add. So it's going to be 0, 1, 0. I'm sorry, 0, 0, 1. Multiply by what am I -2 and add, so it should be -3, -2, 3. By -2 and add that. So it's going to be -3, -2 plus 2. And you take out the middle thing here, I'll just add the middle to the top. And I'm going to get. Oh, this would have worked out swimmingly, didn't it? So I just add the middle to the top. I get 2, 1, -1. So the P I get is E 2, 1, minus 1, 1, 1, minus 1, -3, -2, 3. And actually, that should be the inverse of what this matrix is. So there's that, right? That should be the matrix that changes standard. Or I'm sorry, from B to standard. Okay, part B, find the matrix called A that represents T with respect to standard coordinates. Okay. Okay. Yeah, I did. Do that.
You use the like P, B, P inverse to,
Actually, I think that's the easiest way to do it, really. So here's the way I think of it. You could actually get on your bulldozer and just kind of heavy hand this one if you like. But what we have. Oh, God. This is in B coordinates. Then this transformation is represented by B, right? In B coordinates, you just multiply that B times whatever vector you have in B coordinates, and it gives you its outcome in B coordinates. Everybody okay with that? And here's what we want. We want the matrix A that makes T work here. Right? So, what tools do we have? This is a standard coordinates. What tools do we have here? Well, I know that the matrix that changes, isn't this one that changes B to standard? Right? So B to standard is P. And what changes standard to B?
P inverse.
This is this changes. Oh, actually, I think we did get this right. I think I said it wrong over here. I changed the standard to B. My bad, this is standard to B. And that's the inverse of the matrix that is this thing here. So B to standard is P inverse. And that's what we call it. Let's see, B to standard is P inverse, and standard to B is B. There we go. So this is the matrix that we found over here, right? And P inverse here. Well, somebody tell me what P inverse is.
The original.
It's the matrix you make from the columns of the original. 1, -1, 3, 1, and 0, 1, 1. So the matrix A, this is what this diagram says. This is what you want, right? You want the matrix that in standard coordinates does its magic, right? Well, and I'll do this two ways. Another way to do this is you can start here. Oh, you need to start here this way. P inverse. Doesn't matter what way you do it. So getting A should be do P and then B and then P inverse. So do P first. Remember, this is the order you hit the vector. Do whatever vector you got, do P to it, that changes it to B coordinates. Do B, which is the transformation in B coordinates, and then do P inverse, and that brings it back down to the standard, and that should be today. Well, let's figure out what it is. Start recording this over here. Where this was 2, 1, -1. 1, 1, -1, and -3, -2. Okay, so let's see what A should be. We've done this right. A could be So this should be. Fortunately, these an easy matrix to, these are gonna be an easy multiplication. CP is 2. 1 minus 1. 1, 1 minus 1. And minus 3 minus 2, 3. I think it's this animal. And P inverse is this one, 1, 0, 1, minus 1, 3, 1, 0, 1, 1. Am I okay with it? So let's multiply these two first. 1 minus 1, 0, 0, 3, 1, 1, 1. Let's see, this is pretty easy, I think. This is going to be 2, 1 minus 1. 1, 1 minus 1. It's like the identity matrix, right? Except this, I've now got a row of zeros, so bring back 0, 0, 0. And one more step. Let's just multiply this last bit out. A should be, let's see, 2 minus 1 is 1. 1 minus 1 is 0. Minus 1 plus 1 is 0. This is actually not too surprising. Next row I get, or the next one I get 3, 3, negative 3. Whoops, 3. 3, 3, negative 3, right? Well, that's when I get 3, 2, minus 2. Do you know how to test this? How would you test it? Man, I just put up some matrix with 9 numbers in there. So let's kind of test it at least for a couple of vectors. Actually, you need to test it with 3 linear. What does B do to the vector 1, 0, 0 in B coordinates? It goes to 1, 0, 0 in B coordinates. Everybody agree with that? Because when you multiply this by 1, 0, 0, well, what is 1, 0, 0 in B coordinates? Is 1, 0, 1 in standard. Everybody agree with that? What happens when you multiply A times 1, 0, 1? One, 0, 1, you get 1, 0, 1. So it does what it's supposed to do. It takes that vector to itself. Right? What does B do to 0, 1, 0 in B coordinates? It goes to 0, 1, 0 in B coordinates, right? Anybody agree with me? Well, what is this in B coordinates? It is 1 minus 1, 3, 1. Minus 1, 3, 1. When I multiply this, I get minus 1. Minus 1 is negative 3 plus 9 is 6 minus 3 is 3. And negative 3 and 6 is 3 minus 2 is 1. How about that? Right. And finally, I guess we might check the last one here, 0, 0, 1 in B coordinates. This better go where? What does this matrix do? 0, 0, 1 and B coordinates? Make it a zero vector, right? Do I agree with that? Well, in any coordinate system, the zero vector is a zero vector, right? But what is 0, 0, 1 in B coordinates? It is whatever the last one, 0, 1, 1. And notice it's easy to see when you multiply this by 0, 0, 1, 1. Basically, what you're doing is you're just adding these two entries, so you get the zero vector. So these matrices give you the same thing on a linearly independent set, so they define the same transformation. You could actually use this process that we tested with to actually derive this matrix first principles. But I really think that doing the little computation that we did is much quicker. Everybody okay on it? Any questions on this so far? Okay, let's see what else we've got in store. Okay, is the matrix you got in part B, which one was that? Okay. Is the matrix here? So here's the continuation of the question. So let me ask you two things. A. Oh my gosh, I've got to find that eigenfraction. Or do you? This is the advantage of doing it the way we did it the first time. Isn't that how I computed A? What's true about B?
Diagonal.
It's diagonal, right? There you go. So it is a conjugate, if you will, of a diagonal matrix, so it's diagonalizable by definition. No work is needed to be done. But then I up the voltage and I say, is it orthogonally diagonalized? Very quick answer of no. Why is that?
It's not symmetric.
It's not symmetric, right? No, not symmetric. That is correct. So don't waste your valuable time worrying about that one. Okay. Well, I just don't quit on this, do I? Use the Gram-Schmidt process to refine V to an orthogonal basis for R3. And further refine to make it orthogonal. That'll be easy. Okay, so let's refine this to a basis. So it says, okay, so this is the basis for V. And I said at the beginning, trust me, it's a basis. But we'll find out soon enough because, by the way, if it wasn't a basis, if I screwed this problem up, what would happen in the Gram-Schmidt process? At some point, it would bark out a zero vector. You'd say, oh, that's trouble, right? So let's do this. And by the way, whenever I tell you to do the Gram-Schmidt process, my advice to you is to do it the order that I give it to you, because I usually think about that first. Sometimes there's shortcuts, sometimes it's smarter to do it in a different order, but I actually think about this, and I've got a grade to crowd, so believe me, I'm trying to do you a favor. You don't have to, you can Gram-Schmidt it any order you like, but I would recommend you usually do it the way I have it in there. So, all right, so the first thing I want to do in Gram-Schmidt, somebody was asking me about Gram-Schmidt today too, so let's do that. Take the first one. So that's 101. Okay, there you go. The second one should be essentially the second V, but you gotta adjust it a little bit. So what do we gotta do? We've got to take what we already got, V1 dot U1 over U1 U1. So we gotta take this one into account. So it's the next vector V2 minus V2 dotted with U1 over U1 dot U1. Everybody okay with that? Let me write down what some of this stuff is. The V2 in this case is minus 141. Now let's see, I'm gonna have some kind of fraction here. U1 dot U1 is 2, isn't it? Right? And U1 dotted with yes, let's think I'm on or something. There we go. That's a V2, of course. You dot the new one with the old stuff. V2 dotted with U1 is going to be, well, what is it?
0.
See what I mean? So what does it mean about those two?
They're already orthogonal.
They're already orthogonal in the first place. So big smile, big smile. That works out nicely. This is also V2, which is minus 131. And I guess if I had been paying more attention, I could have looked at it and said, oh, look, that part is 0. Okay, finally, we've got to refine out this last one. For the final one, V3 is V3, essentially, and then you got to kind of take the parts of V3 with the other ones. So it's V3 dot U1, U1 dot U1, U1 minus V3 dot U2, U2 dot U2, U2. Okay, so let's see what shakes out of this. V3 is this mess, 0, 1, 1. Okay, U1 dot U1, I've done that before, that's a 2. U1 dot V3 is what?
1.
Looks like 1, yep. And U1 is 101. Okay, what about V3 dotted with U2? What do we get? U2, it looks like 4. Everybody agree with that? And U2 dotted with itself, looks like, what is that mess? 11? Minus 1. All right, this one's a little yucky, but we'll persevere. Let's see. 0 minus a half in the top. I'm gonna get 1 and just 1 there. And then I get 1 minus a half, 1/2 here, minus. Well, let's go plus here. That's going to be 4/11 minus 12/11 minus 4/11. And I'm gonna rescale this for sure. Let me make sure that I got all that right. 1/2, 1, 5, plus 4/11. So how many 20 seconds is this? This is 9/11. Also 3 is minus 3, 20 seconds. That's 22. Well, yeah, I'm gonna do this 20 seconds. It's gonna be 22 minus 24. And this is going to be 11 minus 8 is. So I'm gonna scale this. Because nobody likes denominators of 22. As cool of a number as that is. So. Okay, what's a good gut check that we could perform right here?
Stop product the two.
That's right, just, I mean, we can quickly see whether or not I've done this right, if these are orthogonal. Like, there's the dot product here and here, minus 3 and 3 is 0. Dot product here is 3, minus 6 is negative 3, and 3 is 0. So I'm really sure I did that right. Everybody okay with it? So this is my new and improved orthogonal basis. And in the next question I ask, further refine it to make it orthonormal. So what do I gotta do here? This one's pretty routine compared to the other. So how do I get my orthonormal basis? That's right, make them all unit vectors. This one I gotta divide by length, which is radical 2. Here the length is radical 11. So like that. And the last one, the length is, looks like it's radical 22. Everybody okay with it? And there you go. So there's my orthonormal basis. By the way, notice when I scale the integers, that's just for ease, right? Nobody wants to square these in that much, right? It's just easy. Okay with them? Okay. Other questions? Yes.
Question 5 on the same.
On the same question 5. So this is last year's exam. The last one ever was. Oh, we had some fun. Consider the matrix 304. So. I can smell a singular value decomposition coming out. Find matrices sigma and B transpose in the singular value decomposition. So that's my first thing. So, okay, so I need a sigma and I need B transpose. What do I need to do to build these things?
Get A transpose and multiply that times A if you get a matrix.
That's good because we need the eigenvalues because the eigenvalues give you the singular values. And once I get the singular values, I know exactly what the sigma looks like. All I need is a singular values to know what that looks like. And what are the singular values? Square root of the positive eigenvalues, right? That's the ones we're going to use. So if you look at, by the way, I always like to know this is 1 by 3. So what side do I expect this to be? Yeah, it's going to be 3 by 3. So this is going to be 304 times 304. So this is, I mean, this matrix is going to be big, but well, 3 by 3 big, but it's not so bad. I'm going to get 9, 0, 12. I'm going to get 0, 0, 0. And 12, 0, 16, aren't I know one eigenvalue for freaking sure. 0 will be one eigenvalue, right? And the reason I know this is because that thing's got a row, in fact, it's got a column, either way you want to cut it, of zeros. That means it's determined as 0. That means one of the eigenvalues has to be 0 at least, right? So let's find the eigenvalues. Well, the determinant of 9 minus x, 0, 12, 0 minus x, 0, 12, 0, 16 minus x. Which equals, let's see, what is this mess? It's 9 minus x times this determinant, which is going to be x squared minus 16x. Then it's 0 times this determinant, so that's gone. Plus 12 times this determinant, which is going to be 0 plus 12x. Everybody okay so far? Okay, so what can I do here? I can pull an X out, but I don't really think that's contributing to proceedings that much. This is going to be minus x cubed. So let me multiply this first mess. Minus x cubed plus 16x squared plus 9x squared is 25x squared. And then I bet you we're going to get some cancellation. Because guess what we get now? I get minus 144x plus 144x is 0. And that had to happen. What are my eigenvalues?
There's 0.
I got 0 twice, right? It's multiplicity 2. I knew there couldn't be another positive one. Anybody tell me why? What are the singular values? There's only one, right? For the positive 25. That's the only singular value, right? So, I guess we'll wait. Remember, sigma has to be the same size as the original A, correct? Yes.
Because the A is a 1 by 3, is that like a hint that tells us there's going to be one singular value?
That's exactly right. There can only be one, because I ain't got nowhere else to put the other ones. I'm out of room, right? 25. If I had another one in there, like say 16, I am totally hosed.
55.
Would it be 5?
It would be 5. So I guess I got a little excited there. 5. There's no place else to put it. Right. So I knew that had to turn out that way. Okay, so now we've got that list. We've got our signal, right? What else do we need? We need V transpose. Okay, how do you get how do you get V?
Basis of the eigenvectors.
Basis of the eigenvectors. And since this is symmetric matrix, even though I know the zeros and I get zeros are repeated eigenvector, I need to get two linearly independent vectors out of that, and it's gonna happen for me. So. But can somebody predict for me what I might have to deal with here? What's one thing that I might have to deal with? Because I don't just want a basis of eigenvectors. What do I need? It needs to be stable. It needs to be orthonormal. And so the zero is going to give me two linearly independent eigenvectors. And I'm willing to bet that when I write them down, they're not going to be orthonormal. So I might have to Graham Schmidt them and fix it up a little bit. All right. But the five, the one that, or I'm sorry, not five, the one that comes from 25 should work with the other ones. So if I subtract 25 from the diagonal here, I get minus 16, 0, 12, 0, 0, 0, 12, 0, minus 9, I guess.
Wouldn't the middle row be minus 25?
Yeah, it certainly would, wouldn't it? Minus 25. Okay with that? And so this is 0, 1, 0. Convenient. And this is say 1, 0, 3, 4, minus 3, 4. And this is 1, 0, minus 3, 4. So I get the 0, 4, 0, 0, 0, 0. And I get eigenvector. What do I get? How about 3, 0, 4? Three that works. Any multiple, that's cool. Now for 0, I like 0 because I don't have to change the matrix. So for lambda equals 0, this is 1, 0, 4/3, 0, 0, 0, 1, 0, 4/3, which is 1, 0, 4/3, 0, 0, 0, 0, 0. Now notice this time I've got two free variables, which is what I expected to happen, right? I need to have two linearly independent eigenvectors here. So x1 plus 0x2 plus 4/3 x3 is equal to 0. That's my governing equation. So an eigenvector looks like x3, x2, and minus 4/3 x3. But because remember, x2 is free, it can be anything. Since it's zeroed out everywhere, you can let it be if you want. So this is x2, 0, 1, 0, plus x3 times minus 4/3, 0, 1. So the eigenvectors, I'll pick this, I'm gonna scale them. Oh, I have been living right. Why did Jimmy get a righteous result here? What's cool about what happened here? They're already orthogonal, right? I got a little lucky with that because the way the equations came out, it just naturally spit out something to me that was already orthogonal. That's cool. Otherwise, if these hadn't been orthogonal, I would have had to run Graham Schmidt on it, but that saves me a step. Everybody okay? So So my basis of eigenvectors should be I erased the first one I got, but I think it was. Was that the one I got for 25? 304. And I got these 0, 0, 1, 0. And let's go minus 4 over 3. 4. I need orthonormal. It's already orthogonal. So orthonormal. So my B should be. So let me be sure that I'm carefully answering the question right. B is 3/5, 0, 4/5. And remember, these should be in decreasing size of the singular values, and the order here doesn't really matter. 0 and minus 4/5, 0, 3/5. And what I'm gonna need, the decomposition is not B, but it's transpose. And that's actually 3/5, 0, 4/5. 0, 1, 0 and minus 4/5, 0, 3/5. There we go. And there's got your sigma. And we can B transpose. Okay. What else we got in the hopper here? Find the matrix U and write out the singular value decomposition. Okay. Yeah, so we'll flip the stuff over here. How do we get U? It goes in front. By the way, what sign use it?
One by one.
Let me ask you this, how many, orthonormal matrices that are 1 by 1 that you know? You know 2 of them, what's the other one? There you go, good, good, that's right, there's 2 of them, right? Has to have length 1, it's either 1 or minus 1, they're essentially the same thing. You can actually see this in action, I can't believe I'm gonna go through this, but I am. If you look at, the original matrix A on 3I, is 1 over sigma I UI, if I remember right. So if you take, in this case, original matrix is 304. And VI is, well, V1 is V1 is this 3/5, 0, 4/5. What happens when you get this? This should be 9/5, 16/5, it's 25/5, which is 5. No, I got this reversed. This is AVI sigma divide. So in this case, this is sigma I, sigma one, U1, which is 5 U1. So U1 equal 1. And there you go. By the way, this works in general, but what happens when you take the matrix A and hit B2 and B3 with it? What do you get? What happens when you take, say, the dot product of 304 in this, dot product of 304 in this, you get zeros, right? That's one of the good things about singular value decompositions is when you go through this process, AVI is sigma VI, when you go through this process, when you're done, it'll start spitting out zeros. And on the other hand, if the dimensions are reversed and you don't get enough columns for you, you have to expand it to a basis, again, using Brandon Schmidt. So here's what I got. And I'm gonna write this up for thematic purposes. And also to help. Next. Here's our singular value decomposition. U sigma transpose, which in this case is 1, but almost doesn't count. 5 0 0 times D transpose 3/5 0 4/5 0 1 0 minus 4/5 0 3/5. Let's see, it's going to be 3 0 4. Perfect. Seems like a lot of rigmarole to go through to get this, right? But there you have it. Right. Okay, so then I am so obnoxious that after making you go through all this, I sort of start over and do it all again, right? Or should we? Yes.
You just transpose both sides of the equation.
That's right. That's exactly right. Take this right here. Let's see. And trans- Yes. B. So remember, if you take the product of these all in the opposite order, so it's transpose B transpose, like at V sigma transpose, U transpose. And these are easy matrices to transpose. So it should be 3 0 4 is equal to B, the original B, 3/5 0 minus 4/5 0 1 0 and 4/5 0 3/5. And let's see the transpose sigma, I guess that would be 5 0 0. And the transpose of U is 1. Right? And you 3 0 4. Perfect. That's much easier than going through the whole process again, isn't it? Okay. Other questions?
We do 6 from fall 2020 final.
Fall 2021?
Yeah.
Okay. Question 6 says, consider the vector space of all continuous functions on the interval -1 with inner product given by that interval. If W is a subspace bound by finding orthonormal. You might have regretted asking to make it orthonormal. Is that Paul 21?
Yes.
That was the Irish class. So. So basically, I have the center product on the set of all continuous functions on the interval from -1 to 1. If W is a subspace spanned by 1x and x squared, find an orthonormal base for W. I'm gonna take some shortcuts. I'm gonna take some liberties. Not some liberties. I'm gonna take full advantage of the calculus. Okay. This is just like the old ordinary Gram-Schmidt process, right? Take 1 to be the first. And there we go. Everybody agree with me? Now. Just X, because 1 and X are one body. Right? Let's be more careful about it. How would Gram-Schmidt really go? It's really the second element minus inner product of X with the first element, inner product with. That's what it is formally. Agreed? But. I don't know, so quickly that's 0. What's it?
The same 21.
Right, but what is it? What is the odd thing about this function that makes that true? It is an odd function, correct? On a symmetric interval. Let me also point out, while I'm at it, because this may come up later. That's also gonna be 0. That might be useful later. Everybody okay with that? So the X in the middle is already orthogonal to the two bookends, right? So I've already got 2 of my basis elements already. So I have now, of course, I haven't normalized, so I've got to go through that. But inner product 1 and x squared, 1 and 1 minus inner product x and x squared, x and x. Now this piece disappears because I've already pointed out that the inner product of x and x squared is 0. So this is gone. Right? Let's figure out what these animals are. 1dx, and so that's just 2. And the integral product of x itself is the integral from -1 to 1 of x squared dx, which is 1/3 x cubed, which is 2/3. So V3 is equal to x squared minus the inner product of I'm gonna do x next. So let's do x squared. Is 0 to -1 to 1 of x cubed. I'm sorry, x squared dx. And of course, notice since the product of these two is the same as the product of these two, you get the same thing. There we go. So you get x squared. This is 2/3 over 2 times 1. So I have x squared minus 1/3. Right, okay with it? Now, what do I have to do? I just have to normalize it. Right. So let's see what this is. The length of 1 is the square root of the inner product of 1 itself, which is the square root of 2. I'm going to need the length of x. This is the square root of the inner product of x with itself, which I think I figured it out. It's 2/3. What's the square root of 2/3? Right?
Okay with it?
And finally, the length this is the obnoxious part, unfortunately. This is the only interval where we have to like really kind of do some stuff. Let me just write squared here so I can just do the inner product itself. This is the integral -1 to 1 of x4 minus 2/3 x squared plus 1/9. If I squared that out, right? And this becomes x to the 5 over 5 minus 2/9 x cubed. That's 1/9 x, which is, let's see, when I put in 1 there, minus 9, so that's a fifth minus 9, which is 4, this is 2. Reckon. So finally, the length of x squared minus 1/3 is the square root of 8/45. One of everybody's favorites. So my orthonormal basis at long last will be one over the square root of 2. X over the square root of 2/3. So that would be something like radical 3/2 times x. And this last bit over that, so it would be radical 45 over 8. There's your orthonormal base. Are you okay with me? Nothing really hard here. It's just, Graham Schmidt, and it's, the last interval was obnoxious a little bit because That's really kind of all there is to it. And I'm not really so focused as much as you getting exactly these right fractions as I am with that, knowing what you're doing and doing the technique right. So. But I guess you've probably seen that on other tests. So, other questions? Yes,
Did you do number 4 on fall 22?
fall 22. Yeah.
Yeah, we just did that.
Or like that.
We did something like it.
Oh, well, those two questions kind of go together because they're like you basically solved for the eigenvalues in 5. So you pretty much.
Oh,
already did.
okay.
Oh, yeah, that's why that question is there. That's right. So the eigenvalues and eigenvectors, I think we did, right? The eigenvalues were 25, 0, and 0, and the eigenvectors were 0, 4 minus 403, something like that, and 0, 1, 0. This matrix is either orthogonally diagonalizable, but not orthogonally diagonalizable, or is not diagonalizable at all, which is true, justified by diagonal in this matrix, orthogonally possible, or explain why it's not possible. So we already orthogonally diagonalized this matrix, but somebody tell me how you can look at it, just put your eyeballs on it and say, yes, it's orthogonally diagonalized. Yes,
It's symmetric.
it's symmetric, right? Is that okay? Is that clear? In a certain sense, that's why symmetric matrices are nice, because I can look at a matrix and say, yes, this is orthogonally diagonalizable. But if you give me a random matrix, I probably can't just look at it and say whether or not it's diagonalizable or not, right? Unless it's orthogonally diagonalizable, because if it's just diagonalizable but not orthogonally, I'm gonna have to actually do some computations and figure out whether it is or not. Okay, other questions? Yes.
Quiz 25.
Like our quiz
Our
25.
quiz 25.
Okay,
The last one.
it is 25.
Question 2.
Question 2, right? This is the 1, 2, 2 and do all that business?
Yes.
Okay, so this is another, this is kind of another SBD kind of problem. So it gives you this matrix here, B. It says compute B transpose B and find the eigenvalues for the singular values. Okay, so that's, I think that's pretty straightforward. It says just compute this and figure out the eigenvalues. All right, and we got the singular. Even I can do this. 2, 2, 4, 4, 2, 4, 4. Now, again, so I'll make an observation here, before I even get started, a couple of observations. The first is, this can only have one non-zero eigenvalue, right? Because the singular values, there's only room for one non-zero. And also, I know for sure that 0 is an eigenvalue, for sure. Because all of these rows are the multiples on top, right? In fact, well, yeah, 0 is an eigenvalue, but we need to get the other one here. So 0 is going to be easy to work out. This looks like death on a hot plate. But if you persevere and do the computation, you'll see that it kind of gets a little bit more warm and fuzzy. This is. Okay, so I've got this determinant to do. This is going to be x squared. Minus 4 minus 8. So it's minus 8x. And a little magic happens because I get plus 16 minus 16, so that's it. That piece. I get minus 2 times this determinant. Let's see, I'm going to get a minus 2x from that. So I get a minus 2x by multiplying these two. What else do I get? I got 8 minus 8, which is 0. That's nice. And finally, I get 2 times that lower left determinant, which is, it's going to be plus 2x. And what numbers do I get? The numbers I get are 8 times 8. So that was pretty swell. So this is, I'm going to do this kind of with a different technique than I did before. I have to show you algebra here. That's 4, 8. Squared x. But okay with them? 4x is 8x, and the rest of it just comes back to this out. Notice I'm carrying a factor of x here, right? So let's pull that x out of everything, and this gives me 1 minus x times x minus 8 plus 8. And this is x times minus x squared plus 8 plus 9x minus 8 plus 8. So the 8's die in the battle. I pulled the minus x out. So it looks like I get an eigenvalue of 9. But notice again, I've got only one non-zero eigenvalue here in this particular situation. So to answer it, the eigenvalues are 0 and 9, singular value. And of course, we only focus on the non-zero single values. Everybody okay so far? Find the matrices sigma and p in the singular value decomposition. Okay, so here, I'll start pulling stuff over here. That's sigma, right? It's the same size as b, and it's just got the single value. Everybody okay with that? Okay, and to get the other one, to get the v, and I think I did ask for v and not v times both. Yeah, for v, need orthonormal basis of Okay, so. We'll do the hard one first. And let me remind us that A was 1, 2, 2, 2, 4, 4, 2, 4, 4. So for lambda equals 9, I get the matrix minus 8, 2, 2, 2 minus 5, 4, and 2, 4 minus 5. Agree? Here's what a mess. So. I am going to, cut this one in half. I'm gonna put, this one, I'm gonna put 2, 4 minus 5 on top. And I'm gonna take these other ones out. When I multiply this by negative 1 and add, I get 0. I get minus 9. I get plus 9. Well, I'll multiply this by 2 and add, I get 0, 9, negative. Oh, that's good. Everybody, okay so far? So now, I can greatly simplify this. 2, 4 minus 5, 0, 1 minus 1, 0, 0, 0. All right. And finally, times minus 4 and add. And so what do I get here? I get the equation 2x1 minus x3 and 0. X3 is the only free variable. X1 minus x3 and 0. X2. X2, thank you. So X2 and X3 are the same thing, and they're half of what X1 is. And so I guess you can get I'm gonna use that for an item back. I'm gonna have the scale. And by the way, you can tell this works if this is in the null space. This row comes this column, gets 0. This row comes this column, gets 0. So I'm going for good. Okay, now the easy one back to 0. And I wonder if I get as lucky as I did last time. Last time I did one like this, it spit out orthonormal, or well, orthogonal automatically. How about that, right? I got down to brass tacks pretty quick on that one. Right? So what do I have here? I've got two free variables, x2 and x3. So the equation x1, 2x2, or 2x3 is 0. And so a typical eigenvector looks like x3, x2, and x1 is 2, x2 plus, no, minus actually, isn't it? So this is x2 times minus 2, 1, 0, plus x3 times minus 2, 0, 1. So I get 2 eigenvectors minus 2, 1, 0 and minus 2, 0, 1. Let's see, and they should both work back. Bang, bang. Yeah, these are linearly independent eigenvectors, but they're problematic. Why?
They're not orthogonal.
Yeah, it is not orthogonal. So I need to get. Notice, of course, as it has to happen, these better be orthogonal to this one. And of course they are, because that row is this column, and we've just seen it works, right? So these are orthogonal both of this, but I've just got to kind of get them straightened out to themselves. So I got to Graham Schmidt these two. So I guess I'll take minus 2, 1, 0. U2 is V2 minus V2 dot U1, U1 dot U1. V2 is this one called these V1 and V2, so we know what we're talking about here. V2 is minus 2, 0, 1. V2 dotted with U1 is 4. And U1 dotted with U1 is 5. U1 is. So let's see what this one turns out to be. This is the top entry, -2 plus 8/5. So that's a total of minus 2/5. 0 minus 4/5. 1 minus 0, which is 1. I'll scale this. You get -2 minus 4. And that should be orthogonal to that. Plus 4 minus 4. Sweet. So here's what I need. Let me go ahead and fix these. -2 over radical 5, 1 over radical 5, 0. This one. I guess that's 45, right? -2 over radical 45. Minus 4 over radical 45. 5 over radical 45. And my other one that I got from the first one, that was 1, 2, 2, wasn't it? And this is from. So. See down there. I think my mistake. Yeah, it works. Yeah, it's all good to go. So, what should be the? We have to put this in the order of the singular value. So this one, singular value 3, this one has to take first. The order of the other two don't matter. Observe corresponding 0. Oh, mix and match here. I'm bad. Minus 2 over radical 5, 1 over radical 5, 0. Minus 2 over radical 45. Minus 4 over radical 45. 5 over radical 45. There's my B. Find the matrix U in the singular value decomposition for B and write the SVD for B. You know what, it's gonna be 1 again, I'm sure of that. But just check this out. So in this case, 1 over sigma 1, which is 3, times A 1, which is 1/3. A was 1, 2, 2, 3, 4, 4. Oh, no. A was the original matrix. I've got a bad nomenclature here. This is A transpose A. And actually, I'm calling my matrix here B anyway, so. So. Times B1, which is 1/3, 2/3, 2/3. And this is just like a dot product right here. It's 1/3 times 1/3 and 4/3 and 4/3. So that's going to be 4, 8, 9/3. So I get 1 again. All right. So the singular value decomposition is B, which is 1, 2, 2, could equal 1 times 3, 0, 0 times this rather forward matrix that we have over here. 1/3, 2/3, 2/3. And actually, that gives you all you need right there, really. Right? Or doesn't it? Well, let's take one of this down. Minus 2 radical 5, 4, minus 1 over radical 5, 0, and oh, it has to be transposed. Get that. That's what we're getting up in. 2 over radical 5, that'll be a negative. 1 over radical 5, 0, and finally minus 2 over radical 45, minus 4 over radical 45, and 5 over radical 45. And these are just here to complete a north and normal basis. Really, the only thing that matters, you see when you multiply the matrix up, the only thing that matters is the top row, right? This times this 1, this times this 2, this times this 2. There you go. Any questions? Okay, another question.
Just quickly go over LU factorization,
What's that?
the LU factorization.
Oh, yeah, well, we could do one like that if you wanted.
I just didn't see any on the exam, so.
Um, see. when you do the LU factorization. One's convenient. First thing to do. let me see, that's- Okay, so let's try this one. All right, so. How about this, 2 minus 4, 4 minus 6. Let's do this. 6 minus 9 is 7 minus 3. And finally. -1 minus. What's the first thing to do if you want to do an LU factorization of a matrix?
Use an echelon.
Right, but you don't go all the way, right? I mean, because what we did in our LU factorizations is that we don't do row swaps, and we don't really have to divide out by stuff. So let's go with this top row here. It's predicted for next line forms. Well, so let's reduce it to an echelon form. This is going to be 0, -3, and add 3. It's going to be -5, 23, like that. That looks right. Multiply by 1/2 and add 0. That's going to be -6. That's going to be 10. How about that? That's going to be -. So here's the first pivot, right? And what we do as we go along here. So what we want to do is we want to build the L piece from the lower triangle from the pivot columns, right? So L. What should L be, or what should the first column of this be?
So 1, 3, -1.
Yeah, you want the ones, right? So I think it should be 1, 3 minus 1/2, right? Right, because this is the first pivot. And of course, L is the lower triangle matrix, right? And by the way, what should the size of this be?
3 by 3.
Right, L, so. A is what, 3 by 4? So L should be. And what should U be?
3 by 3.
3 by 4. So you match the size of this one. L should be lower triangular, so I already know this. Gotta be, right? And if the lower triangle is gonna be like this. And what about well, let's kind of see where this takes us. How about the U part? How do we build that?
So 30, this is the echelon form of the A, right?
Mm-hmm. So, where's my next pivot? This one looks good, doesn't it? So let's reduce this on down to 2, 0, 0. Right, so this next column should be, actually, so what should my next column here be? 2? It should, because it's the next pivot, right, so it should actually be 1, -2. And then I've got, no choice for the rest of it, so I've got my L. And we'll see if this works. See how to do it. This is going to be 3 minus 5, 3. When I multiply this by 2 and add, I get 0, 0, and that's going to be 5. Everybody good to go on that? And it looks like this works. How about that? Let's see. Did I get that right? Oh, you. Yeah, that's right. Yeah. And so what we did is we built the pivot columns and we've got to scale them down to make sure that we've got ones on the diagonal. So notice that if you have L, which has first scaled pivot column, second scaled pivot column, and then that comes my echelon form here that I got. 0, 3, minus 5, 3, and finally 0, 0, 0, something 5. If you multiply this out, you get, well, of course, this row, you go through that, just spits out the top row here. No problem there. Then this one gives 3 times this plus this, 3 times this plus this, and so forth. So that should give me a 6, minus 9, 7, and minus 3. Good, got my second row. And finally, the most complicated, minus a half, minus 2 plus 1. So let's see, that's going to be minus 1. That's going to be 2 minus 6 is -4. Is that right? Yeah. This is going to be minus 2 plus 10 is 8. And this is going to be 1 minus 6 is -5, 5 is 0. So it's just an algorithmic procedure there. Okay. Other questions? Yes.
Give me your 30-second definition of linear independence.
Oh, I can get it quicker than that. This is a set of vectors. It could even be infinite. If I think if we the equation. A1 B1 plus A2 B2 plus AK BK equals 0. Forces A1, A2, and all the coefficients 0. Right. But we have many ways of thinking about this. If these are column vectors in Rn, we can put them in there, and it means that right, so if we make columns out of these K vectors, they're linearly independent if, you know, they span columns, or not span columns, but well, what does it tell me about pivots?
That each one is. That they're all critical
Okay,
in creating the basis.
okay, that's right. So there's lots of ways to do it. Linearly independent means not linearly dependent, and what it means to be linearly dependent is one of these vectors in here is a linear combination of the others. So there's lots of ways to think about it. How many of you have more than one testimony? Anybody? You guys can be happy and start the purity of Kuykendall ends. Yes,
For Paul, final exam 2021. Question 1, could you explain, part B, J, K, and L? Or just J and L?
this is final, 2021. State Cauchy-Schwarz inequality. Is that, if I get that right?
Yeah. But that's B. Then J.
Anybody know the Cauchy-Schwarz inequality? So we gotta, I mean, we should be at least somewhat precise in the language and talk about the playground we're playing in, so. I want to be really clear. Given by this. Whatever with Cauchy-Schwarz inequality is.
That's the guy.
Center equal to what?
The absolute value of the length would be times the absolute value of the length of W.
All you need is the length of the and the length of it, because the lengths are already. But yes, that's certainly the spirit of it. Did you say K as well?
Just L.
L.
Literally straight.
If U is an orthogonal matrix,
Straight.
what is U used to do? Transpose. By the way, what does it mean to be orthogonal? Means all the columns are orthogonal, but you need one more, there's a subtlety that we need to throw in there too.
The product of each column all equals 0.
Well, but there's a special shape. It has to be square. It has to be square. It has to be square. And so in this case. What should be? Yeah. It's the what, these are square matrices, and when you multiply this by transpose, if you've got orthogonal, so here's what happened. Let me give you an example. This is probably worth looking at. Look at this matrix. Well. We'll call it U. Um, This matrix has matrix has orthonormal columns. Everybody agree with that? The lengths of those two columns are one, and the dot product of them is zero. Agree? So let me show you what happens. What's U transpose? This is 1/3, 2/3, 2/3, 2/3, minus 2/3, 1/3. Am I cool with that? Now, notice that. U transpose U. Would everybody agree that U transpose U is 2x2? No, it's 2x2. This row times this column, I get a 9, 4 9s is 5 9s, it's 1. If this row times this column, it better be 0. I get 2 minus 4, I'll make 2, 0. Right? What happens if I do? Can somebody tell me what's going to happen if I do it in the other order? Or if I do U transpose? What's the size of this going to be?
3 by 3.
What's going to happen now? Well, let's see. What I'm U transpose, so I'm going to have 1/3 and 2/3, so that's going to be 5 9ths. Then I'm gonna have 2 minus 4 is minus 2 9ths. And I guess I'll so 2 4 9ths. Looks like. Second row, that's gonna be 2 minus 4 minus 2 9ths. That's gonna be 4 8 9ths. That's going to be 4 minus 2 is 3 9ths. And finally, the last bit is going to be 4 9ths. And so the 2 9ths is 4 minus 2 is 2 9ths. And finally, 4 and 1 is 5. Not the identity, because now it's apples and oranges, right? So it was important here, we had U transpose U in that direction. But if the matrix is square, then you're good to go, right? Here it's not square. Tell me a couple of things about U transpose there. Symmetric, right? And it's 5 minus 2 4. Yeah, so you might see if you can find the eigenvalues. Okay, but in the case of the square, the U transpose is the identity. And of course, in the case of square, it doesn't matter what order you do it, because basically, if it's orthogonal, then nodes that have orthogonal columns in a square. And so it's transpose and its inverse are the same, so it doesn't matter if you transpose or you transpose you, it's the same thing as the other. But here, when it's not square, in one direction you get the identity going to the smaller size, the 2 by 2. When you go to the bigger size, you get a mess. Okay. Other questions? Yes.
That's going to be 2 question 1 chart. And
Given the n by n matrix, n by n matrix A, so let's do this. So m rows in columns, what is rank A plus the dimension of null A to P? The terms you know. Or what?
the rank only.
Okay, what's rank nullity, let's say?
Is that like, that's just the rank A plus dimension of null A is just a number of columns.
Right. So this is rank nullity. Can somebody explain to me basically what it works? Yeah,
Rank A is like the number of linearly independent columns, and then the dimension of null is the number of linearly dependent columns that has to add up.
I would say, so why don't we say it this way, rank A is the number of pivot columns. And the dimension of the null space is the number of free variables, which is the number of non-pivot columns. So if you put your pivot column and non-pivot columns together, you get the number of columns, that's essentially it. We have a twist here. Null A transpose. I really wish this were an A, don't you? Then it would be easy. But I do a little prestidigitation. My rank nullity, this is true for any matrix, right? This should work. This should be the number of columns of A transpose, which is what? M. All right, everybody agree with that? How does this help me here? Let me ask you another question. What's the relationship between rank A and rank A transpose? They're the same. That's the key. So this is equal to, so let's kind of go through it here. Is everybody on board with this application right now? Right? Everybody okay with it? But this thing. Is rank. Rank the matrix and transpose it. So. Rank A. Plus then. No. And P. Is also equal to 1. Okay, other questions? Yes,
That same exam, question 1 part G.
G. Let's see here. Okay, so, yeah, it's gonna take me longer to write this question down, we'll see. But, okay, so you've got this linear transformation marked, R3 to R3 and a 3x3 matrix such that TD is a 3. Okay. If R is a solid in R3 with volume V, what is the volume of T of R? A fancy R is a solid in R3 with volume V. What is the volume? Yes,
Would it be 1 over the absolute value of the determinant times the original volume?
not 1 over, I mean, you're on the right,
It's
yes.
just AB times the.
So what happens is, this is, the volume. It's the original volume times the determinant of A. Right? If I go far enough. Absolute value, right? Determinant can be a little dangerous, because it can be negative, right? For example, you might take, I don't know, like a pyramid, and linear transformation might make it grow and turn it upside down. You might have a negative determinant there, but the volume is still increased by whatever the factor of the determinant is. Okay, any questions on that?
I got one question.
Sure.
All same exam, question 2 from part.
All 2022,
Yeah.
question 2.
2.
Oh, right. I'll tell you right now. So here's a quick way to do this. I'm gonna write the system down. And we can solve it if you like. It's not too difficult to solve. Did you have any problems?
No, I didn't have any problems.
Right, so let's look at the system itself. It's 4x1. Something like that. Let's say 4 minus 2 is 5. Three. Minus X 5. 3, 2, 5. It was something, that's right. Now, you solve this, you get the thing, and so a typical solution. Looks like that. No way is the solution set of vector space. Can somebody tell me why? What's the first thing you've got to have to do? You have to have the zero vector, right? And there's no way, I mean, look at the first equation, 0 equals 3, it doesn't work. So the answer is no. Yeah, when you have like a homogeneous, those are always nice little vector spaces, right? No problem there. When you have ones that are not homogeneous, that's when you get in trouble.
Okay,
Have you had differential equations yet?
no.
You're gonna see this, if you do, but then you'll have particular and homogeneous solutions to these equations. So hopefully that will look somewhat familiar when you get there. Other questions? Okay, I expect you guys to show up tomorrow and give it a smack down. Sure.
Yesterday I had a meeting. I set my alarm for 5:55. I woke up at 6:06. My alarm was going off, but the volume was off. So I couldn't hear it.
I'm turning on like.
I literally just got.
How are
I
you
literally
like?
just got.
Oh,
woke up
hi.
and said that.
Or 5, and just go over. I hope my body just feels like it's the panic wake up anyway. When I have to wake up early, I always wake up and like, did I miss it?
You know, like I turned like my phone screen like was showing that the alarm was going off.
But the volume.
But there was-
I've had that happen to me. It's the worst.
And like. Dude, that was the biggest like panic.
Yeah, like everyone, we do that in that one.
That's
Pretty easy to find the eigenvalue. Eigenvalue 25, blah, 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 you know.
Okay. Okay. Thank you very much.
Yeah, that one is so easy that it's hard. I mean, I understand that a little bit, right? It's a number here.
Yeah,
Think of it as a 1-by-1 matrix. Right?
I think I get scared.
Sure.
Let's say in that video.
Anything, sure thing. Anything else, y'all?
I'm all right.